Today, we're diving into the invisible forces that quietly shape the entire periodic table: nuclear charge and atomic radius. These two trends explain almost everything about how elements behave: bonding, reactivity, metals versus nonmetals. All of it starts here. In an atom with many electrons, each negatively charged electron is simultaneously attracted to the positively charged nucleus and repelled by the other negatively charged electrons. The nuclear charge, Z actual, refers to the total positive charge located within the nucleus, which is equivalent to the number of protons. The higher the number of protons, the higher the nuclear charge, the stronger the attraction of an electron to the nucleus. Screening effect is the reduction in nuclear charge due to the core electrons that screen outer electrons from the full effect of the nucleus. It is represented by the Greek letter sigma. The higher the number of core electrons, the higher the screening effect, and the weaker the attraction of an electron to the nucleus. The net effect of the nuclear charge and screening effect is known as the effective nuclear charge or net nuclear charge, represented as ZeFF. The higher the effective nuclear charge, the stronger the attraction of an electron to the nucleus. The formula for effective nuclear charge is that it is equal to actual nuclear charge minus sigma, the screening effect. Slater's rules are a semi-empirical method for calculating the effective nuclear charge for any electron in a multi-electron atom. They do this by providing a formula to calculate a shielding constant, sigma, based on an electron's position in the atom's electron configuration, which is then used to estimate Zf using the formula Zf equals Z actual minus S, where Z actual is the actual nuclear charge. The rules involve grouping electrons and assigning different shielding contributions from other electrons in the same or inner shells. The nuclear charge increases as the number of protons increases. The screening effect remains relatively constant as the number of core electrons remain the same. Hence, the effective nuclear charge increases. The nuclear charge increases as the number of protons increases. The screening effect also increases as the number of core electrons increases. The effective nuclear charge increases as increase in nuclear charge is only partially offset by the screening effect. This is due to the poor screening effect of the electrons in the d orbitals. Note that this increase in effective nuclear charge is less than increase across the main group elements. D orbitals are more angular or less spherically symmetrical as compared to S and p orbitals. Thus, the screening effect of d orbitals electrons is less effective. D orbitals are also associated with a relatively high principal quantum number, where n is more than or equal to 3. Both factors contribute to d orbital electrons being more diffuse, hence resulting in poor screening effect. F orbital electrons also have poor screening effect for these reasons too. Atomic radius is defined as the distance between the nucleus of an atom and its outermost or valence electron. The measurement is difficult because electrons are in constant random motion and do not reside in orbitals with fixed boundaries. Instead, atomic radius is estimated by measuring the distance between the nuclei of two adjacent atoms and then halving the distance. The metallic and covalent radius, as well as how to calculate them, is shown here too. The difference between the three is that atomic radius, more precisely covalent atomic radius for nonmetals, is defined as half the distance between two identical atoms held together by a covalent bond. Metallic radius. Metals don't form directional covalent bonds. Instead, they create a lattice with delocalized electrons. Here you take half the distance between the nuclei of two adjacent metal atoms in the metallic lattice. This distance is usually longer than a covalent bond because metallic bonding is weaker per bond. Van der Waals radius. This is the do not enter boundary when atoms aren't bonded at all. just touching. It is defined as half the distance between the nuclei of two identical non-bonded atoms. It's the largest radius because you're measuring atoms in their non-bonded contact state.